Welcome to grade 10 trigonometry. We're going to be defining the trigonometric ratios today, and I know this word is very new and possibly daunting to you, but for now I want you to clear your mind and have no fear, because we're just going to explore those the first three letters of that word, trigonometry, triangles. To be more specific, we are going to be dealing with right-angled triangles. In grade 10, you will only be able to apply trigonometry to right-angled triangles. So please don't fall into the trap of trying to apply this new knowledge you're about to gain to triangles that are not right-angled. Right. If we look at this bottom left vertex of this triangle, we can call that angle of the triangle theta. Now all I want you to do is to look at the three sides of this triangle, and let's talk about their relation to theta. Directly opposite, so theta has the two rays that form theta are two sides of the triangle, but that side that is directly opposite the angle will be called the side that is opposite to theta. It's as simple as that. Then if you look at the ray that forms the angle theta, the horizontal line of the triangle, we can call that side of the triangle the side that is adjacent to theta. Now you may think the other part of the ray of the angle of theta is also a side that is adjacent to theta. And that is correct. But we can't call two sides of the triangle the adjacent side. So this yellow side is, of course, the hypotenuse. And the hypotenuse will always lie directly opposite the 90-degree sign. So the easiest thing to do when you're faced with a right angle triangle is to first identify and highlight your hypotenuse. We like to use abbreviations or purely just the first letter of each of these words to save ourselves some time. So the opposite side can be called O, adjacent can be A, and hypotenuse can be H. It's important to remember that any acute angle in a right angle triangle will have one side that is opposite to the angle and two sides adjacent to the angle, one of which will always be the hypotenuse. Hence, we have three sides in this triangle in relation to the theta, that being opposite, adjacent, and hypotenuse. Remember, your triangles may differ in size, and they may even rotate to be viewed from a different angle, so you should just take care to carefully notice your hypotenuse and which side lies directly opposite your theta, and then the third side is usually the adjacent. Right. Let's consider this triangle for a moment. Once again, it's important that it is a right angle triangle, and let's pretend theta is that bottom left vertex. Right, if I tell you that this is a typical right angle triangle with a hypotenuse of 5, it's a lovely Pythagorean triple, 3, 4, 5. Let's think about the ratios of these sides, or let's think about the opposite, hypotenuse and adjacent values of the sides in relation to theta. Let's have a look at opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. If we fill in the corresponding values, we'll see that opposite over hypotenuse will be 4 over 5. Adjacent over hypotenuse will give you 3 over 5, and opposite over adjacent will give you 4 over 3. Easy peasy. Since those are simplified fractions, we call those ratios. Let's have a look at another triangle. This triangle is also right-angled, and it also has an angle theta. Thus, that small triangle and this big triangle are similar triangles, which means their angles are the exact same size and their sides are in proportion. So, say I double the size of this triangle, and now my opposite is 8, my hypotenuse is 10, and my adjacent is 6. let's complete let's find opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. If you fill in the relevant information and simplify your answer, you will see that O over H, A over H, and O over A all simplify to be the same value again. Now, the conclusion we can make is that this will happen always for any right-angled triangles that are similar to each other. So if you are given a specific angle, theta, alpha, beta, 35 degrees, 60 degrees, whatever angle you are given, if that same angle is repeated in another right angle triangle, then those ratios O over H, A over H, and O over A will always simplify to be the same value. So since we know that the ratios will be consistent for all similar triangles, we can now attach definitions to these three ratios. O over H will be called the sine ratio of theta. This can be abbreviated to SIN, but we still say sine of theta. I know you'll be tempted to say sin, but I think it's a pet hate of mine and many other teachers when you hear the word sin instead of sine. The next ratio that we can define is going to be called the cosine of theta. That can be simplified to cos of theta, COS. And then the last one, tangent of theta, is the ratio O over A, which can be reduced to just tan theta. These three ratios are to be memorized, and they will work in all right-angled triangles always. A lovely way to remember them is that sine is O over H, SOH, cos is adjacent over hypotenuse, CAH, and tan is opposite over adjacent, TOA. If you combine all of that together, you get a very cute word, Sokotoa. It sounds like an exotic island where I'm sure we'd all love to be right now. Where are you going for holiday? I'm going to Sokotoa. Right. Let's apply Sokotoa to this right-angled triangle, ABC. Sine is opposite over hypotenuse. What is the side that is opposite to the angle theta? AB, and the hypotenuse of this triangle, AC. So sine of theta is AB over AC. Opposite and the hypotenuse. O over H, AB over AC. What about cosine of theta? Cosine of theta is adjacent over hypotenuse. So adjacent to theta is CB, while the hypotenuse we've already established is AC. Last but not least, tan of theta will be opposite over adjacent. We've already established that O opposite is AB and adjacent A is CB. Voila! Right, moving on to an example. If we need to write each trig ratio in terms of DE, EF, and DF, we need to have a look at the angle from which we are working. Look at A, sine D. That means you need to pretend that theta that we covered in the previous slides is there at the vertex D. Let's discuss this. Oh, first things first, remember Sokotoa. Sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. So for sine being opposite over hypotenuse, but we want the sine of D. So what is the side that is opposite to D? EF, of course. And what is the hypotenuse of this triangle? DF. The hypotenuse is always opposite the 90 degrees, so sine of D is EF over DF. Now let's go to the cosine of D. Cosine SOHCAHTOA, CAH, is adjacent over hypotenuse. So which side is adjacent to angle D? It can't be DF because that's the hypotenuse, so it must be DE. And so cos of D is DE over DF. Then last but not least, we have tan of D, which is the opposite over the adjacent. We've already established that EF is opposite and adjacent is that green side of the triangle DE. But wait a minute. What if you were asked to answer this exact same question, but with F as your angle of reference? Well, let's have a look. We've got to ignore the fact that we've defined opposite and adjacent in question A, B, and C. We need a new opposite and adjacent value. If you look at F, opposite to F, excuse the purple arrow, it's meant to be coming from F, not from EF. Opposite to F is the side DE. So sine and adjacent to F is not DF because that's the hypotenuse, so the adjacent side to angle F will be EF. Sine being SOHCAHTOA, sine is opposite over hypotenuse. We now know that DE is opposite and the hypotenuse is DF. Cos F is adjacent over hypotenuse. So what's adjacent to angle F is the side EF and the hypotenuse is DF. And then last, the easy peasy one is tan of F is opposite over adjacent. Opposite is DE and adjacent is EF. Last example before you move on to your homework is, what if the triangle is labeled slightly differently? This touches on what we covered yesterday, the different ways to name a triangle. If we are now asked to write down sine H, once again, we remember, where are we going on holiday? SOHCAHTOA. Sine is opposite over hypotenuse. What is the side that's opposite to vertex H? Of course, it is that baby H, and the hypotenuse in this triangle is called K because it is the side that is opposite K. And K represents 90 degrees. Cos, the cosine of H, is adjacent over hypotenuse, so SOHCAHTOA, and adjacent to H will be L. Hypotenuse is still K. Tan, tangent, SOHCAHTOA. We're going to need the opposite over the adjacent of H, and that is going to be baby H over baby L. Let's answer the exact same questions, but with respect to angle L. Opposite to angle L will be baby L, and the hypotenuse will be K. Cosine of L, SOHCAHTOA, adjacent over hypotenuse. Well, now adjacent is no longer L because we are now referring to L, so adjacent must be H, and the hypotenuse remains K. And then tan TOA, opposite over adjacent, opposite to angle L is side L over side baby H. You've got this.